Every single run now lands somewhere informative. No more redundant sample, no more wasted simulation. So the shift is conceptual instead of form-leading function. One observation we found striking: the advantage shows up more clearly in aerodynamics than in structural mechanics. Deep generated models are great at proposing globally novel shapes, large creative leaps in geometry. Our framework is good at the opposite, locally refining where the model is uncertain. Going through this exact pipeline, we found that UQ-guided augmentation produces meaningfully more informative samples than conventional random augmentation.
Ladies and gentlemen, welcome to a new deep dive series today about three-dimensional geometric augmentation guided by engineering uncertainty, today with Yongmin Kwon from Narnia Labs. Yongmin is a PhD student at KAIST and an AI researcher at Narnia Labs, splitting his time between academia and industry and working on research that bridges the gap between the two. His work sits at the intersection of AI and mechanical engineering, spanning generative design for engineering, agentic AI for autonomous design, and design for manufacturability. Today, he'll be presenting his recent work, Three-Dimensional Geometric Augmentation, Guided by Engineering Uncertainty. And with that introduction out of the way, Yongmin, welcome to the show, and the stage is yours.
Thanks for the intro, Joseph. Happy to be here. So the work I'd like to work through today is called Three-Dimensional Geometric Augmentation Guide by Engineering Uncertainty. It's a long title, but the idea is actually pretty simple. We let the model tell us where it's unsure, and we use that to guide how we generate new shapes. I'll unpack what that means over the next few slides. So let me start with the background of this research. In engineering design, simulation is essential for verifying performance, but high-fidelity simulations are expensive. They take significant time and computing resources. To reduce this cost, deep learning-based meta models have become a standard approach. The idea is simple: train a neural network on simulation data and use it as a fast surrogate model. But here we hit a bottleneck. Building a reliable meta model requires a lot of training data. And since each simulation is so expensive, real industrial projects rarely have enough. This is data scarcity problem, and it is the starting point of our work. So the natural reaction to we don't have enough data is, let's make more. Take the shape we have, deform them, augment them somehow. That's standard practice. And to be honest, that's the approach I worked on myself in my previous research. Our group published DeepJet last year, a synthetic data set of jet engine brackets with around 2,000 shapes. Quite a few people are using it now. But here's what I realized while building it. We were generating shapes that were geometrically diverse, but that didn't mean they were informationally diverse for the model. And these two figures show exactly why. Look at the figure on the left. You can see three sampling strategies. The first two, random and diversity in design, both try to spread samples out in the design space, and in the top row, they do that well. The shapes look geometrically diverse, but look at the bottom row. The same samples projected into the performance space, they are all collapsed into the same small region. So even though we deliberately push it for geometric variety, the performance information is still narrow. The third column, diversity in performance, is what we actually want. The samples spread out where it matters. In the performance space, this is the kind of coverage that gives the model new information. And the figure on the right makes the same point with a different data set. The grid on top, uniform sampling in the design space, look well distributed, but the scatter on the bottom showed what that becomes in performance space. Clearly non-uniform, clearly clustered. Designing diversity in the design space simply doesn't translate to diversity in performance. So the implied the implied assumption of the conventional approach that geometric diversity means informational diversity doesn't really hold. Design space and performance space are different spaces. Sampling uniformly in one does not mean covering the other. We need a method that targets performance diversity, not just geometric diversity. In practice, this means you might run expensive FEM or CFD simulation only to find out the model already knew what was going to happen. That's the redundancy we want to avoid. And this is the turning point of the whole work. So if previous slide set up the problem, this slide is the answer. The one-line message is at the top. Augment where the model is uncertain, not everywhere. That's the whole idea. Instead of trying to spread samples uniformly in the design space and hoping they cover performance space, we let the model itself tell us where the gaps are. And we focus our limited simulation budget exactly on those gaps. In practice, this becomes three steps. First, we explore the regions of high uncertainty. We ask the model, where are you unsure? A well-trained surrogate can actually answer that. It can give us a spatial map of its own knowledge gaps, what we call epistemic uncertainty. That map is our compass. Second, we use that map to guide augmentation, not random deformation, targeted deformation toward the region where the model is uncertain. Think of it as the opposite of randomness, where new shape we create is purposeful, aimed at a specific gap in the model's knowledge. And third, we maximize data efficiency. Same simulation budget as before, same number of expensive FEM or CFD runs. But every single run now lands somewhere informative. No more redundant samples, no more wasted simulation. So the shift is conceptual. Instead of form leading function, generating shape first and see how they perform, we flip it. We let function lead form. The performance gap drives the geometry. That's the core idea of the whole research. Let me walk through how the actual pipeline runs, step by step. Now, let me put everything together and present our overall data augmentation framework. The process operates as a continuous cycle consisting of three main steps. First, we train deep ensemble model as a surrogate model using a small amount of initial data. Next, we use this trained model to estimate the uncertainty across the design space. Then we specifically target regions with high epistemic uncertainty. We applied FFT technique to deform and augment shapes in these knowledge deficient areas. Finally, we perform simulations to label these newly augmented shapes, add them to our training set, and retrain the model. By repeating this cycle, we can efficiently improve the model's performance while minimizing the need for massive data. So this is the slide, what I want to tell. Let me walk through it from an engineer's perspective. The things to remember is the simulation budget doesn't change. We are not asking anyone to run more FEM or CFD jobs. What changes is which shape those jobs land on. First, we start from a small set of seed shapes, data scarce setting. The model has barely explored the design space. Second, what conventional FFT augmentation does. You take those shapes, move the lattice point around, and you get geometric variety. The shapes look different, but as we saw earlier, geometric diversity is not the same as performance diversity. Many of these new shapes are redundant from the model's perspective. You burn expensive simulation on regions the model already understands. Third, what our method does. Before we deform, we ask the model, where are you uncertain? And we move the FFT control points more aggressively in exactly those regions. The simulation budget stays the same, but every single run now lands somewhere the model genuinely needed. The practical value then is simple. With the same FEM or CFD budget, random augmentation tends to revisit redundant regions, while UQ-guided augmentation targets the uncertain one. Same cost, much better information. And one observation we found striking, the advantage shows up more clearly in aerodynamics than in structural mechanics. We think it's because aerodynamic performance is much more sensitive to local surface features, small pressure sensitive region on the car body. And our framework naturally focuses on exactly those local area of high uncertainty. So if there's one line to take from the slide, it's at the bottom. Don't augment everywhere. Augment where the model does not know. And to make this concrete, here's what the actual augmented data sets look like for both DeepJet on the left and DriveAirNet on the right. In each panel, the leftmost column is the original training data, and the rest is what our method generated. Two simple observations. First, the shapes are visibly different from the seed, not just minor perturbation, but genuinely different geometric variations. And second, look at the small histogram next to each shape. Those show the performance distribution. After augmentation, those distributions get broader. We are covering performance regions the original data didn't reach. And the same pattern holds for both domains, structure and aerodynamic. Same framework, no domain-specific tuning. The one-line message is right at the top, and I'll repeat it once again because it's really the takeaway. I'd like to leave with you, don't augment everywhere, augment where the model does not know. These are three things I'd highlight as the core contribution. First, a performance uncertainty model that lies in the same lattice space as the FFT control point. So uncertainty and deformation share a spatial alignment. They speak the same coordinate system. Second, uncertainty-driven control point placement. The deformation magnitude isn't random and isn't uniform. It directly follows the model's epistemic uncertainty. And third, cross-domain generality. The same framework works on a structural problem like DeepJet and an aerodynamic problem like DriveAirNet without any domain-specific tuning. That was actually one of the most encouraging results for us. On the practical side, the takeaway is simple. Same simulation. On the practical side, the takeaway is simple. Same simulation budget, more informative samples. Engineers don't have to run more expensive FEM or CFD jobs. The expensive run they already do just go to better places. And looking forward, what I'm most excited about is connecting this with generative AI. Deep generative models are great at proposing globally novel shapes, large creative leaps in geometry. Our framework is good at the opposite, locally refining where the model is uncertain. Combining the two, global exploration with local refinement, feels like a natural step toward what I'd call performance-aware generative design. So that's the story I want to share. Thanks for listening. Let's check out a quick demo of the actual workflow, and I'll walk you through it after. So if you imagine you're an engineering sitting down to use this for the first time, the workflow is essentially three stages: setup, then uncertainty visualization, then the actual augmentation. Stage one, the setup page. Uh, this is the first thing you see, and the idea is that everything you need to configure on uh, lives on a single page, but no hidden menus, no wrong config files. Four components side by side. The first is the dataset. In this work, we use DeepJet and DriveAirNet as our two examples. DeepJet for the structure bracket case and DriveAirNet for the aerodynamic car case. You can see the panel below the dropdown actually change depending on what you pick. It tells you what physical quantity you're predicting. For the bracket, it's bone miss stress. For the car, surface pressure on the body. And the total data set size is 50 samples. We are being honest about the fact that this is the data scarce setting. That's the whole reason we are here. The second is the prediction model. The key things is in the architecture. One matter is that the model has to be able to report uncertainty. Without that, the whole framework can work. That's what the little green label is signaling. Ensemble of three members, epistemic uncertainty available. In this mockup, it's a deep ensemble of three networks, but in principle, it could be any model that gives you a epistemic uncertainty estimate. The third is FFT and augmentation. This is where you control how aggressively you want to augment. And the n per axis slider at n equals to 5, you get 125 control points around the object. Smaller n means coarser deformation, bigger n means finer. And the augmentation per sample slider tells the tool how many new shapes to generate from each seed. 10 in this case, meaning 50 seeds become 500 augmented shapes. The fourth is the simulator. This is what runs in the background to label the new augmented shapes. The mockup shows ANSYS, Altair, and OpenFOAM as options, not because we've integrated all three, but because in a real engineering team, this is the part that has to be flexible. Different companies use different servers. The framework itself doesn't care which one you plug in, as long as it can produce a label for the new shape. Once everything is set, you hit next, and you move into the part that I think is actually the most interesting. Now, stage 2, the deep ensemble UQ visualization. This is the part I'm probably most attached to because it's the moment when the abstract idea of the model has uncertainty becomes something you can actually see. The page shows the bracket geometry in gray and around it and inside it, you see a cloud of purple dots. Those dots are the FFT control points, and here's the key detail. The size of each dot is the epistemic uncertainty of the model at that location. Bigger dot, more uncertain. Small dot, more confident. The dot size are deliberately scaled this way, so the spatial pattern is easy to read at a glance. And once you have that picture, something interesting jumps out. The central control points carry larger dots than the edge ones. That actually makes physical sense. The central control points have more deformation freedom, so they affect a wider range of possible shapes, and the model has the weakest grip on what happens there. The edge points are more constrained, so the Models' predictions are tighter and the uncertainty is smaller. And the tool is interactive. You can drag to rotate it and scroll to zoom. Hover over a point and see the actual sigma value plus the point ID. So it's not just a one-shot rendering, it's a tool an engineer could explore. The reason I wanted this view in particular is that when you're talking to non-experts or even to engineers who haven't worked with uncertainty quantification before, it's much easier to say, look, the model is showing exactly where it's unsure, than to talk about epistemic variance in abstract terms. The picture does the work. Stage 3, FFT plus augmentation, the actual generation. Now we're at the payoff. The same lattice from the previous phase is now used to deform the geometry, but the deformation isn't random and it isn't uniform. It's driven directly by the uncertainty map we just looked at. Control points with high uncertainty move more aggressively. Control points with low uncertainty barely shift. So the new shapes are biased toward the legions the model did not know yet. You can see this at the top of the page, bracket again, but now overlaid with deformation zone. And then below, the actual augmented sample. The header leads 10 per source and 50 sources, total 500 brackets. So you've taken your 50 seed shapes and produced 500 augmented brackets, each one geometrically valid, each one targeting a place the model needed more information. Look at the thumbnails. Each one is subcolored. That's the predicted stress, Bomis's stress distribution on the new shape coming from the Altair or ANSYS one. So even before running the real FEM simulation, engineer gets a preview. You can scan through the 500 shapes, spot the one that look interesting and decide. At the bottom, there's a download dataset gem button in there. That's how it would actually hand off to the engineer's downstream pipeline. They pull the augmented data set and feed it into whatever server they are using. One thing to mention before we move on, this is some mockup mainly built to work through the workflow visually, but the workflow itself is real. And going through this exact pipeline, we found that UQ-guided augmentation produce meaningfully more informative samples than conventional random augmentation. On the DeepJet bracket case, the R-scale value of the trained surrogate model improved by 14% over random augmentation, and on DriveAirNet, it's actually outperformed even the case where we added more ground truth data. The full numbers and analysis are in the paper, so I won't drill into them here. So that's the demo. Thank you for my talk. I really enjoyed walking through this video. If anyone wants to follow up on the work or chat about generative design in engineering, my email is on the slide. Thank you.